let's talk about representations of functions of multiple variables as power series. Well, these are the special forms of some of the most well-known elementary functions and their power series representations. Well, you guys went through a long process to get all this by finding multiple derivatives, maybe by the fourth derivative, and then finding a pattern, then looking at the, what's it called, the radius and interval of convergence, which is really a fancy way to say domain of the function, all right? Because in the end, the amount, if you add as many terms on the series, actually the series converges to the values of the function, to some intervals for some of them, for all real numbers, for some of them with some restriction, with some restricted values. Okay. Typically, you would see this with an X right here. However, I decided to give you this summary of power series with a U, because what if you have a composite function? What if this U instead is an X squared, an X cubed? Well, so that actually, we need a little more than that. Well, just to briefly review, before getting into our exercises here, let's use the back side of the page just to briefly review how did we do this in Calculus 2. For instance, find the representation for f of x equals to x squared e to the x cubed. All right? And no, I'm not going to take 5 derivatives for this, because the first derivative is a product rule, which will generate 2 terms, which will make us do 2 product rules and then 3. And I don't want to do that. Instead, we're going to use a substitution. Hopefully you got to see this way. Okay, so first of all, identify the elementary function. Well, in this case, the elementary function is the exponential function. However, this is not just e to the x. This is e to the it's a composite function, for which I'd rather call this x squared e to the u, where u equals to x squared. And then I'm going to call the power series for this function e to the u, x squared, which is sigma n equals 0 to infinity of u to the n over n factorial. However, we have u equals to x squared. What do we do with this? Back substitute for u. X squared sigma n equals 0 to infinity of x squared to the n power over n factorial. Okay? Well, let's simplify the rule inside. Actually, I'm going to have this x squared inside of the series x to the 2n over n factorial from n equals 0 to infinity. And I'm going to, yes. That's what I meant, but not what I wrote. Yes, thank you. Cubed, 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 and 3. Right? Thank you. Okay. Change the same. Thank you. And then just use laws of exponents. Sigma n equals 0 to infinity, x to the 3n plus 2 over n factorial. That's what we did in Calculus 2. All right? So rather than taking too many derivatives, just do a use substitution for the composition. For the series, back substitute, and put everything together. All right? Let me do another one. Because for the next one, that's the sort of thing you're going to do for one of the take-home quiz questions. How about f of x equals to 1 over 3 plus x squared? All right? Let's get a power series for this function. Now, number one, we need to identify the function that looks like this one. Let me go back to the summary of power series. Does that function look like any of the ones on the screen right here? Which one? It's like a geometric series. However, be careful for the geometric series case. In the denominator, it doesn't matter what you have in the numerator. I have a 1 because that's the general form. However, this guy must be a 1, and there has to be a negative in between always. We need to work that in the example we have over here. Okay? So, So number one, to fix that issue, I'm going to multiply by or divide by 3 in both numerator and denominator. All right? So 1 divided by 3 equals 1/3. 3 divided by 3, isn't that 1? And then x squared divided by 3, that's x squared over 3. And there's still a plus in between that I still need to take care of. Okay, that 1/3 in the numerator, I'm going to take it outside as a coefficient. I'm going to write this as 1 over 1. Oh, how do we generate a negative here? Do you guys agree that this is minus negative x squared over 3? And now this looks like 1 over 1 minus u. We're ready to set that u. So that's 1/3, 1 over 1 minus u, where u equals to negative x squared over 3. Okay? So now we're good to go and use the power series for this rational function, which is a geometric series. Okay? Let me go back to this real quick. I don't want to make any silly mistakes. Yes, simply u to the n, right? So that is 1/3 sigma n equals 0 to infinity u to the n for u equals to negative x squared over 3. Okay? And let's back substitute for u. 1/3 sigma n equals 0 to infinity u to the n, well, in this case, negative x squared over 3, quantity squared. But let's use laws of exponents here. Oh, well, not to the second, it's to the n, right? So be careful here, because negative 1 to the n will actually give us this alternating factor, this negative 1 to the n. X to the 2 to the n, that's x to the 2n divided by 3 to the n. However, let's get that 1/3 and put it together with the, what's it called? With the, so that is sigma n equals 0. Okay, do you guys agree? This 3 is the same as saying 3 to the first power. So that means we can combine in the denominator 3 to the n times 3 to the 1 equals 3 to the n plus 1 together. Alright? Let me do that. So this will be negative 1 to the n, x to the 2n, over 3 to the n plus 1. And that is our representation for this function. Is that the sort of thing you did in Cal 2? After the long way of finding many derivatives, that was like a 2-page problem to solve. Well, we have formulas for it. Now let's apply this to functions of multiple variables. Okay, so express the function f of x, y, z equals to x cubed y to the 7, z to the 4, e to the x squared, z to the 6 over y cubed as a power series. Alright? Well, this function looks crazy, but I mean it's just identifying the elementary function, which function is it? The exponential, alright? And well, it's not just e to the u, it's e to the something. So we can call this, so f of x, y, z equals x cubed, y to the 7th, z to the 4th, e to the u, where u equals to x squared, z to the 6, over y cubed. Okay, let's call the sigma n equals 0 to infinity of u to the n over n factorial. Alright? For u, where u equals x squared, z to the 6, y cubed. Okay, let's just substitute into the u. That means all this. This over here. Alright? X cubed, y to the 7th, z to the 4th, sigma n equals 0 to infinity. All this madness here, x squared, y to the 6th, over z to the 7th, no, that's z to the 6th, y to the 3rd, to the n, over n factorial. Same as we did before, all we're going to do is raise or multiply the power n to different powers of x, y, and z. That's it, that's all we do. Okay? So, what is this? No, not yet. X cubed, y to the 7th, z to the 4th, sigma n equals 0 to infinity. X squared to the n, that's x to the 2n. Z to the 6th to the n, that's z to the 6n. Divided by y to the 3n times n factorial so far. Now let's combine together powers of x. How about 2n plus 3? 6n plus 4. And therefore 3n minus 7, because essentially that 7 would go to the denominator to be combined with the powers down here. So sigma n equals 0 to infinity of x to the 2n, z to the 2n plus 3, z to the 6n plus 4, everything divided by y to the 3n. Minus 7 times n factorial. And that's our power series for a function of 3 variables. And well, notice I omitted the details. It's actually a Maclaurin series because it's centered at 0 for all variables. We're not going to get into those details. All right? So, yeah, I like how they look like in power series representation. They look cool. All right, well, let's have a look at one more example, and then we get to work with limits. Okay. So now we're going to do the reverse. We're given a function. Well, we're given a power series, but they're asking us to find the function represented by this series. And yes, it may look crazy, but there's actually one piece of information that would give away the function that we're working. Okay, let's review the different power series. Okay, so guys, exponential function has an n factorial in the denominator. The sine function has a 2n plus 1 factorial. That is an odd factorial because it's an odd function. You can relate it to that. Cosine function has a 2n factorial. That's an even factorial, even powers of u. That means you can relate to the fact that it's an even function. The arctangent function is similar to the sine function, but it doesn't have the factorial in the denominator, right? So that's how we can distinguish between the two. Okay, so which of the elementary functions is closest to the one we have on the notes? Cosine, is that 2n factorial to give it away? Yes. Okay, so but what do we have to do? Look at the power. We need to go back and obtain 2n powers of every single variable. Okay, we have a 2n right here, but we have the plus 5. We have an 8n, but we need to turn that into a 2n. We have an n, we need to turn that into 2n somehow. Okay, here's the trick. The trick here is to sigma n equals 0 to infinity. I'm going to write x to the 2n times x to the 5th by laws of exponents. That's the 2n I was looking for, at least for the x variable. Now, how do we turn the power of y, which is n, into a 2n. Well, this is the same as saying y equals to n multiply by 2, but divide by 2. How about that? Right? And number 3, for the denominator, well, 8n is a multiple of 2n. That's actually 4, right? So this is x to the 4 times 2n. All right? So I'm going to do, okay, times 2n factorial. This x to the 5th, which doesn't have any n's, can go outside. All right? And I'm going to regroup all this. So I'm going to write, so that is x to the 5th, n equals 0 to infinity, x to the 2n. Okay, let me do parentheses. X to the 2n. I know it's silly to have too many parentheses, but it's going to be very useful for visual purposes. Here, I'm going to take out the 2n as a power. Isn't that the same as y to the 1/2 to the 2n? Because power of another power multiply the powers, all right? If we're just using this property backwards. Divide this by x to the 4th raised to the 2n. 2n factorial. And we have all we need. Yes.
It's z on the bottom.
Oh, yes, it's z. Thank you. Okay, so do we have a potential rule for u? All of this will be our u. All right? I'm going to write this as one single quotient having a common exponent. Yes?
What do you do about the alternating factor?
Oh, yes, I forgot the alternating factor. Thank you. Yes. I was solving to the powers, ending -1 to the n. Thank you. Yes. So I'm going to write a common fraction, one big fraction, x to the 5th, sigma n equals 0 to infinity, -1 to the n, and I'm going to write x, y to the 1/2 divided by z to the 4th, with parentheses instead. Everything raised to the 2n over 2n factorial. All right? And from here, we can identify our u, which is that big quotient. So, this is x to the 5th, sigma n equals 0, -1 to infinity, -1 to the n, due to the 2n over 2n factorial, which will be turned into a cosine function shortly. But this u is x. Okay, y to the 1/2. Isn't that really root of y over z to the 4th? And let's express this sum, this infinite series, as the cosine function. X to the 5th, cosine of u, where u equals x root of y over z to the 4th. And simply go back, substitute x to the 5th, cosine of x root of y over z to the 4th. And that is the function represented by the series. Right? So you're going to be given a couple of each for today's take-home quiz. What time is it? So actually this is the end of the section, isn't it? Okay, let me give you the notes for limits. Okay. Okay, notes. Okay, 2.2. Mm-hmm.